When I'm talking about a capacitor across a battery, the work done by this battery to move a charge in this circuit is QV. And the amount of charge that is stored in the form of potential energy in this capacitor is half of QV. So where did the other half go? Anyone answer? If QV is the work done by the battery and the energy stored by the capacitor is only half of the times of the work done by the battery, where did the other half go? It went in the form of what?
Lost in the form of heat.
It's lost in the form of heat. Okay, good.
It got transferred in the form of energy.
Heat, yeah, heat, exactly. But if I replace this capacitor with a resistor, what is going to happen? Well, first of all, let's say the work done by the battery is QV only. Then what is the energy stored by this resistor? Will it be half QV? Will it be half of QV?
No, sir, maybe it will be a different value.
It will be a different value, but why? That is the important question. I don't want your answer. I don't want the magnitude or any variable answer. Just tell me what will it be. Will a resistor store anything in it? Is a resistor used for storing charge?
No, sir.
No,
No,
it is not. So it is not going to store any energy. All the work which is done by the battery across a resistor is lost in the form of heat. Yes.
So can you the people in take waiting room?
People are waiting in the waiting room.
Yes, sir.
No, it seems no one is waiting. No one is waiting. Check. Okay, now we check. Okay, the waiting room has been disabled since morning. Anyone can enter, no problem. Okay, that's the thing. So again, I'm going to continue. I'm saying that this resistor is there. And in case of a resistor, we can see that it is not going to store any charge. So before we understand the depth of this, let's understand how a battery itself works. Okay, how is it able to produce this QV or whatever across a circuit? Okay, how is it able to produce that? So let me just, you all know this symbol. Okay, this is a symbol of a battery. Yes or no?
Yes, sir.
I will just make it a little bit big so that I'm able to show it across the camera. Now in a battery, we have all types of chemical substance. What are the substances that we have? We have plates, copper plates, we have acid, and the mixture of these conductors and acid, okay, they produce a certain force. What they do is they produce a certain force. So always remember, there is a force in the battery, okay, which is produced because of the chemical reactions within it. And let's call that force FB. Okay, let's call that force FB. Now you will say, why only in this direction? I'm just trying to consider a positive charge. You know what is the charge on this side of the terminal of a battery? It is positive in nature.
Positive.
And this is negative in nature. Now I am just considering a positive charge in the circuit. I am not considering a negative charge. I'm not considering an electron right now. So it's a positive charge. So the force on the positive charge due to this battery will be what? If I connect this across a resistor like this, how is the positive charge going to flow? It is going to flow from this side and it is going all the way to the negative side. So you can see the force on a positive charge is from the negative terminal to the positive terminal. Can you agree? Can you agree? Yes or no? Now, if that is the case, can I say that positive charges are accumulating on this side of the terminal? Because you can see all positive charges from this circuit are coming towards this side, this positive terminal. And you can also imagine that the negative charges will be will be accumulating on this side of the terminal of the battery. So you will see that there is more number of positive charges being developed here, and there is more number of negative charges being developed here. In that case, what will happen? Can anyone tell me? Can anyone tell me what other force will be developed within this battery? If there is a positive charge here and a negative charge here, and they are becoming stronger and stronger, what happens?
Potential difference.
Yes, potential difference. True, true. Very good answer.
Electric
What
field.
else? Electric field. Okay, electric field. Yes, potential difference is the right answer. But potential difference develops after what? Before what? It will develop only when electric field is there. Okay. So electric field's direction will be from what? You remember? Electric field
Positive
direction will be
Positive to negative.
Positive to negative.
positive to negative. Positive to negative. So can you see what is happening here? This is my electric field. And this is the force on a positive charge in a circuit. Okay. So if I am telling that I am considering a positive charge right in between this and I take it separately outside like this, can we draw a free body diagram of forces on this positive charge? Okay. So I can say that this is FB. Can I say this is FB? Okay, I can say that.
Yes, sir.
And I also know that the electric field is in this direction. I know the electric field is in this direction. So if the electric field is on this direction, from left to right, it's going like this. Will there be any force on this charge due to this electric field? Will there be any
Yes, sir.
force? Yeah. And how do we get that force? I said that E is equal to what?
F by
Force
Q.
F by Q. Force experienced by a test charge. And so can I say the force is equal to E times the charge? That is electric field times the charge. So what it will become? Where will it have a force? Will it have the force in the direction of electric field here? And can I say that is
Yes, sir.
Fe, which is basically my electrostatic force? And the electric static force can be defined as Q times capital E, where E is the electric field. Okay. So this is a free body diagram. Now, once you have drawn this, we can basically play with it. And just for your information, this battery right now is not connected to a circuit. So what is that state? What is that state called? If a battery is not connected to a circuit, what is going to happen? It's a steady state. It's a steady state. It's not a dynamic state. It's not a dynamic movement here. There are no charges moving. Okay, there are no charges moving for now. Just consider it to be a point charge, which I have assumed, and I have assumed that the force on the battery is always in this direction for a positive charge, and there's electric field right in between because of the charges that are first before itself accumulated by whichever manufacturer has made it. So they are manufactured in such a way that this is entirely positive, this is entirely negative. There's an electric field being developed right on this side. Because of that, if we consider a point charge, it's going to have an electric force right on the right side. Okay. Has everyone understood till here?
Yes, sir.
When I tell you steady state, okay, can I say in the steady state, when this battery is not connected to any circuit, can I say that the force of the battery, force developed on the charge Q of the battery, will be equal to the force of the electrostatic force? Can I say it is equal? Can I say it is equal? Okay, it is equal, and that is equal to Q times E. Q times E. Why? Because there is no movement of charge. The force on any point right in between will be equal. Force due to battery and force due to the electric field of the battery. Okay. In steady state, this is going to remain true. The force of the battery on a positive charge and the force on this charge due to electrostatic force will be equal. And the magnitude is Q times E. Please pay attention. Q times E. Now, when we studied potential difference, when we studied the second chapter, potential, okay, what did I say? Work done is equal to change in potential. Do you remember that? I said that work done was equal to change in potential. Do you remember delta W is equal to delta U? Yes or no?
Yes, sir.
And
Yes, sir.
this delta W was what? External external. Please remember. And the change in potential is also equal to a negative of work done. Negative of work done, but by which term? Which work? Electrostatic work. Work done by,
Electrostatic.
yes, please remember this relation. It is important. And there is something else also going to add in this relation right now. So you, which we had done previously, but I don't think you might remember. And so I'll be trying to derive this equation in such a way that now onwards we'll remember another term. You tell me what will be the work done by this battery. Work done in our mechanics. What is the work done? Isn't it force into displacement? Can I say it is force into displacement?
Yes, sir.
Force into displacement. Of course, now if I'm talking about the work done by the battery, what is the force I'm talking about? I'm talking about FB. Am I talking about FB? So I will write FB here. Let's consider the displacement to be some D. Okay, let's consider it to be like this. So now you know that this force FB in steady state has a magnitude which is equal to Q times V. So just substitute that. What will you get? And it is amazing what we reach into Q times E. But we know that, okay, if I'm moving opposite, if I'm moving in the direction of electric field, okay, there is a potential difference. There is a potential difference being developed. And if I'm moving in the direction of electric field, the potential difference will drop. So can I say minus dV by dr is equal to E? Yes or no? But if I'm considering a positive charge which is moving opposite to the direction of electric field, can I say the potential increases? Yes or no? Can I say the potential will increase opposite to the electric field?
Yes, sir.
Yes or no? So if I remove the derivative of this, if I remove the derivative, what can I get? I'll get V, I hope you all can see it. Yeah. V upon some distance D will be equal to E. Of course, I am taking it to be positive because opposite the electric field, the potential is going to be equal to positive. It will be positive. So can I say that potential here is E times D? Can I say potential is E times D? If I know this, if I know that the potential is E times D, and you can see from this formula Q into E into D, can I mix E and D and call it V? Can I mix both of this?
Yes, sir.
And that is what exactly I will be doing. So the work done by the battery can also be written as Q into E times D, and that is equal to Q times potential difference. Q times potential. I derived this, but if you all had to remember, I didn't have to derive it. So please remember that work done by external force is equal to change in potential. The external force we are talking about here is a battery, of course, because if I take two positive charges like this, I'm going back to the lesson I taught you in potential. If I take two charges like this, and I say that this charge over here, Q, is a positive charge which is fixed, and this is some Q naught which I have brought from infinity. Okay, if I consider both of these charges to be positive in nature, okay, then the electrostatic force on this charge, on this test charge, because of this fixed charge right here, will be repulsion. Can you agree with me? Repulsion will be repulsion. Yes,
Yes,
or no?
sir.
So I will call that repulsive force as F times Fe, that is electrostatic force. But the force which will be applied personally by someone like me in bringing these two charges together can be called as external force, F external. So that is the same concept in this battery. If I am considering a positive charge, okay, I'm considering a positive charge, which is the work which is done by the battery against the electric field, then the work done by the battery is simply Q times V, and this work done by the battery is basically the external force, external work done. So finally, with all of this that we have just derived, I can come up to a simple expression that just tells me that the work done by the battery is simply what? Q times V. And so now I want you to remember that the work done by the external, W external, will be equal to, of course, the change in potential, U, will also be equal to the negative of the work done by the electrostatic force, but this will also be equal to Q times V. Will also be equal to Q times V, considering that the work done by the battery is the external, is also equal to the external work done. Is it clear? Is it clear?
Yes, sir.
Yes, sir.
So if you all have understood this, if you all have understood that the work done by the battery is Q times V, which we had also derived. That is the reason I had asked you the first question, the amount of work done by the battery in a capacitive circuit. In any circuit, the work done by the battery is Q times V. Remember it. When you look at a battery, remember it. It's fun. It's okay. It's not fun for those who don't have any interest in this, but somehow we can actually write the energy, the basically things what the environment can produce in terms of heat, energy, and whatever. If we are able to write it on this board, it's a beautiful thing, and there are people who have contributed to this. So we're just trying to study that. Don't always have this mind of my test scores need to be high. Of course, your test scores need to be high, but that has to also be somewhere related to understanding the concept and appreciating the concept. Okay, so enough of me talking. So the work done by the battery is Q times V, and since I've spoken so much, I hope you'll remember this. And so V, that the potential difference developed within this battery right now, can be written as work done by the battery upon Q. This is simply what I have written by rearranging this term. Okay, so the work done by the battery in moving a charge Q between the battery terminals, okay, is WB equal to Q times V. Potential difference is, of course, the potential between these terminals, not anywhere else. Okay, this potential right here is also known as EMF. What is it known as? EMF, electromotive force. And why do we call a potential electromotive force? Why do we call it? We call this electromotive force because of the force which is developed by this battery due to chemistry. Okay, due to the plates and the acid which is developing this force. Okay, in ancient times when the battery was developed, not ancient, I will not call it ancient. There's no other word which is coming in my mind. And so in those times when the battery was first developed, they thought that the charges basically moving is due to some force, and that is how this term electromotive force got coined up. But electromotive force is basically just potential difference. It's just potential difference. Okay, so I hope you all have understood. But right now, all this derivation was done basically in steady state. In steady state. So what should be your next question? What should be your next question? If I was talking about steady state, let's talk about dynamic state. So let's say that there is this battery right here, and now it is connected to a circuit. Let me say it's a circuit, some circuit. Can imagine anything. And now I don't need to explain again. Why will there be a force from this point, negative terminal, to the positive terminal? And of course, there will be electric field right here in the opposite direction, capital E. Okay. Now, once we connect the battery to the circuit, once we have connected the battery to the circuit, the positive charges are sent from where? From the positive terminal to the negative terminal. Look here. Look here. The same concept I'll be applying in semiconductors also when we study PN junction. Okay. So listen to me. As soon as you connect this to a circuit, what is going to happen? Isn't this positive charge going to come here Isn't it going to come here and meet this negative charge? Similarly, a negative charge will come from here and meet a positive charge here. What happens when a positive charge meets a negative charge? They neutralize. They neutralize. You agree with me? Yes, no?
Yes, sir.
Are you all able? Yeah, okay. So if they neutralize, can I say that the charges on both these plates are somehow depleting? They are reducing. They are reducing in nature. Okay, because they are connected in a circuit. Positive charges coming here, meeting a negative charge, neutralizing. Similarly, negative charge coming here, meeting a positive charge, neutralizing. So if they are neutralizing, what is going to happen? Can you all tell me? To the force of electrostatic force, what is going to happen to the electrostatic force? We know that the electrostatic force E, which I have not shown here, and of course it is in the direction of the electric field for now. You can take that. So E is equal to F by Q. And so electrostatic force F will be how much? Q times E. Well, won't this reduce? If the charge is reducing on these plates, will the force reduce? Yes or no?
Yes, sir.
Yes, sir.
And if the
Yes, sir.
and if this force is reducing, then of course the force is reducing. But if the another point is, if the charges are reducing on these plates, what else is going to reduce from these two? Can you see something here? What will reduce? Will E reduce or will FB reduce? I'm saying the charge is reducing. Charge produces the electric field. Charge reduces. What reduces then? The electric field reduces. If the charge reduces, the electric field will reduce. And so the force will reduce. The electrostatic force will reduce. So if I have to draw again a positive charge right over here, if I have to draw a positive charge right over here, of course the force developed by the battery is going to be constant. I will say that it is constant because there is chemical reactions going on inside. But due to connection of this battery, the force of electrostatic force Fe is going to reduce. And so now we can see that Fb is greater than Fe. Fb is greater than Fe. So once this is achieved, once this condition is achieved, every positive charge that is here will be taken from the battery and pushed here because of this force Fb. It's going to be pushed here. All the positive charges are going to be taken by this battery and thrown right here because of what? Fb. There are
Yes,
some
sir.
chat. Yeah, there is some doubts. Okay. So, but in actual, only electrons are moving. So, how is it neutralizing? No. See, listen to me. I have just considered a positive charge here. Listen to me. It is not just electrons moving. Okay, that is a wrong concept. If electrons are moving, protons also are moving. If negative charges are moving, positive charges also are moving. But while deriving this expression, we can consider only one so that it is easy to explain. It is easy to derive expressions. I will come to this doubt. This doubt will again be developed in semiconductors and we'll be able to understand that much better. Okay. If there is a positive, if this is a positive terminal right here and this is a negative terminal right here, I can say that there is positive charges going from the positive terminal to the negative terminal. Also, I can say that there are negative charges and neutralize. Okay, that is the explanation. I can give it to you right now. But when we get into PN junction diodes and stuff, I'll be actually zooming or I'll be actually giving a detailed explanation of that. And that I think is in your second term. Okay, right. Okay, so we'll come to finding out equivalent resistances again. Let's try to find out The equivalent resistance, some more practice. Okay, equivalent resistance here, over here. Tell me the equivalent resistance between A and B. If the resistances are 6 over here, 6, there's another one 6, there's a 12, and there's another 12, and there is an 8 ohm. Find out the equivalent resistance between A and B.
4 ohms.
Any 4 ohms. Okay, good. Any other answers? So someone said 4. Any other answers? Okay, what will be your strategy to solve this sum? What will be the strategy? There doesn't seem to be any response, so I'll continue. Look here. From this point here and this point here, can I say there's a blank conductor right in between? So can I just make that one point? Can I do that? Similarly, can I say that the point over here and the point over here is same thing? Is the same thing, just a blank conductor. Even here it is the same issue. So let me name that points. E, F, there's a G, there's a H, there's an I, and there's a J. So now I can say that E and F are 1 point. And also I can say that G and H are 1 point. And there's also I and J. Okay, there's also I and J. So let's start. From G to E, how many resistors are going? From G to E, there's one resistor right here. From G to H, there's another resistor. No, right? G to H is a point. H to E, there's one resistor. We'll write it here. So this is done 6. This is done 12. Similarly, E to F is just 1 point. F to J, there is a 6 ohm resistor. And then we have F to J. I to J is simply a point. I to H, there is 8 ohms. So I and H are going to have 8 ohms resistor. Okay. I to H has a 8 ohm resistor. And is there any other resistor? F to J is one already done. And F to I is a 12 ohm resistor. So here you can see 6 and 12 are parallel to each other. 6 and 12 are parallel to each other. Yes or no? This is going to be A and this is going to be B. So now I can say, let's consider this 6 and 12. So 6 parallel with 12 is how much? 6 into 12
4.
upon 6 plus 12. That is going to give me 4. Similarly, 6 and 12 here is also going to be 4. So 4 plus 4, 8. So ultimately, I can just rub this entire sum of resistors here. And I can say that there is an 8 ohm resistor because it was repeating twice. So 4 plus 4, 8. 8 parallel with 8 is simply R upon N. Here N is 2. So I can say 8 by 2. And so that is going to give me 4 ohms. So the equivalent resistance over here is going to be 4 ohms. Okay. Let's do another one. Let's say this is 6, this is 6, this is 1, 3, and this is going to be 2. Find out the equivalent resistance between A and B. Do it quickly. All of you all please participate. Even if it is easy, no problem. Just participate.
2 ohm.
2 ohms. Anyone else? Any other answers? Is there anyone else who is listening to me apart from one person? Doesn't look like, I don't know. Okay, so of course you can redraw this. You can see here 6 and 6 are parallel to each other. 1 and 2 is in series with each other. And the entire thing is parallel again with 3. I can just redraw this like this. This is 6, this is 6. Okay, this is 1, 2, and this is 3. So 6 parallel with 6 is how much? 3? Yes or no? 6 parallel with 6. I will write here. Is 3. And 1 plus 2 is in series here. So that will be 3. 3 parallel with 3 is what? Sorry.
1 point.
1 minute. Mistake. This 3 will not come here. This 3 actually comes from here to here. Yeah. 6 parallel with 6 is what? 3. And this is in series 3. Yes or no? So ultimately, what will get across this to this? We'll get 6 ohm resistor. Yes or no?
Ohms.
We'll get 6 ohm resistor across this entire black lines which I have drawn. Just rectify that. And 6 parallel with 3 is 6 into 3 upon 6 plus 3. That is 2 ohms. That was going to be 2 ohms. Let's do one interesting one. We have 4 minutes left. Let's try this out. For those who have done this, you all can message in the chat. What is going to be the resistance across this cube? If I say there's a resistor here, there's a resistor here, there's a resistor here, a resistor here, a resistor here, a resistor here. Tell me what is going to be the resistance across this point A and across this point B.
5R/6.
It's going to be 5R/6. Okay, someone answered 5R/6. Anyone else? Okay, so to solve this sum, first you denote it with all the names. That is, forget this A here. Forget this B here. Let's say this A, this is B. Okay, whatever. C, D, E, F, a G over here. This letter be H. Okay, have I named all? Yeah. So if I do this, if I am able to do this, what we should be able to find out is if I have to find out this equivalent resistance between A and G, most simple thing is just take a highlighter for now and just see what all paths can you use from A to G. Can I go to G from this point A like this? Okay, let's consider only the first step. I can go like this. I can go this way also. I can go this way also. Now, the interesting thing is that the potential across A and B, just remember, just listen. Potential across A and B and the potential across A and D and the potential across A and E, are they going to be same? Yes or
sir.
no? Why they are going to be same? Why are they going to be
That-
same?
They are equipotential points.
Why do you call them equipotential? Why do we call them
Symmetry.
equipotential? Symmetry. Okay, symmetry. But also, can I look at it in this way, that since all the the first part from A to B, A to D, and A to E all have resistances which are equal in magnitude. Of course, I'm considering it to be equal in magnitude. Can I say that these are equipotential? Can I give that result? So in that way, I can say that this point E, D, and B are equipotential. There seems to be only 1 minute remaining. And so please try out this sum. Please try out this sum. We will continue in the next lecture. We will continue in the next lecture. I hope you all have understood some of the concepts which have been taught today.